Hey, welcome back. In this video, we're going to introduce the concept of three-dimensional vectors. And quite honestly, if you have experience with two-dimensional vectors, you feel somewhat comfortable with three-dimensional space in general, this won't be much of a long shot. We just need to make sure that you understand that the same properties that applied to two-dimensional vectors get translated into the three-dimensional vectors. All right, our setup for the three-dimensional vectors is actually exactly the same as with the two-dimensional vectors. We're going to let C in this case be a scalar. And again, what is a scalar? All it is just a number. When you're dealing with vectors, vectors have these two or these three dimensions. A scalar just has one dimension, a magnitude of sorts or a scale. And this notation right here just means it's going to be any real number whenever we write it down here. And by the way, just in terms of notation, R is the set of real numbers that you can describe along a number line, right? A one-dimensional number line. R2 would actually be the rectangular coordinate system, so it's a two-dimensional number system. And R3 is just another way of describing our three-dimensional number system. In R1, which we just say the real numbers, you just need one number to describe an element of the real numbers. In R2, you need these ordered pairs for the X and Y, right? Or two coordinates. And in R3, we need three coordinates. And our description of the vectors is no different than two-dimensional. We have this in its component form right here. We have three different values that describe along the X, the Y, and the Z axis for each of these vectors. First up, we wanted to talk about vector addition, and it's again exactly the same as it is in two dimensions. If we want to add any two vectors, we just add their component parts together. So this would be U1 plus V1, comma, U2 plus V2, U3 plus V3. And again, this will end in a vector, which we just add these component pieces together. And I won't write it all back out, but just put a little notation here. If we're going to subtract, it'd be exactly the same thing. We subtract their component parts. So that's vector addition and subtraction. Then we have scalar multiplication. Again, exactly the same. When we multiply a vector by a scalar, what we do is just multiply each of the component pieces by that scalar. So this is C times U1, C times U2, comma, C times U3. And finally, we should discuss the magnitude of a vector, which is like the distance from the beginning to the end of a vector, or the strength of a vector, depending on the application. We denote that in exactly the same way. So the magnitude of the U vector is what you expect. It's really the same thing as the distance formula in three dimensions. We take U1 squared plus U2 squared plus U3 squared, and we square root that to find the magnitude of the vector. All right, let's do a couple quick examples to ground ourselves with these three-dimensional vectors. First, we have U equals 2, negative 5, 1, and V is negative 3, 4, 6, and we're being asked to find the vector that is defined by 3 times our vector U plus the vector V. The first thing I would do right out the gates here is find this term right here, this 3 times U. And this is really easy. Again, all I'm going to do, I won't even write it out in its detail. I'm going to multiply each of these component pieces by 3. So this is going to be a 6. This is a negative 15, and this is a 3. So that's 3 times the vector U. And then if I want to add that to vector V, well, I'm just going to be adding these two vectors together. So 3 times vector U plus vector V is going to be 6 plus the negative 3 here, comma, negative 15 plus 4. And then my 3 plus the 6. And that would give me 3, negative 11, 9. One thing to note as we move forward, it's going to be really important to understand that when we do vector operations, when do we get out a scalar or when do we get out a vector, right? So when do we get out just a number or when do we get out a vector? Whenever you're doing scalar multiplication or vector addition and subtraction, the result will always be this vector right here. If we do something like magnitude or dot product, what we're actually going to get out is a scalar. All right, in this example right here, we're being asked to find the vector and find its magnitude. for the vector that starts at 1, 3, negative 7 and ends at 8, negative 4, negative 2, it's actually important to point out that we really do need to know the starting point and the ending point, right? If we had a point just in even 2 or 3 dimensional space, we had a point that was right here and a point that was right here. It matters, are we going from here to here or here to here? Because that direction would be different, right? The direction is actually very important. So we're starting here and going to here. What we need to describe in component form is the direction in the x-axis direction, y direction, and the z direction. So we're going to do, for instance, the x component, or that first component, would be 7, because it would be from 1 to 8. So what we need to do when we're finding this vector is we're going to take this ending point and subtract the values of the starting point. More specifically, just to write it out, we'll call this one vector v just for fun. That first component is going to be 8 minus 1. The second component is going to be negative 4 minus 3. So negative 4 minus 3. And then negative 2 minus negative 7. And just performing these operations here, we have that vector v is going to be 7, negative 7, 2 plus 7 is 5. And importantly, as I write it here, I just want to speak this out, how this makes sense. If I'm going from here to here, and again, I could try to graph this out, and I have tried, it doesn't look pretty, so we'll just kind of play in our mind's eye here. To go from this point to this point, I have to increase along the x direction 7 units. To go from 3 to negative 4 in the y direction, I actually would be going backwards 7 units to go from a positive 3 down to a negative 4. And then to go from a negative 7 to a 2, I'm actually increasing along the z-axis 5 units. And then to find the magnitude, again, it's really easy. It's exactly the same as 2-dimensional vectors. All I'm going to do is square each of these component parts. So I get 7 squared plus negative 7 squared plus 5 squared. And I'm taking the square root of that, which would be 49 plus 49 plus 25. And when I plug that into my calculator, take the square root, it's a little bit bigger than 100. This comes out to be about 11.09. Again, those two examples didn't provide us anything really radical. It was just important to say, hey, everything we've done in 2-dimensional vectors is the same in 3-dimensional vectors. We just have these 3 component pieces. But as you'll see when we move forward, there are actually interesting things that we can do in more than 2 dimensions that we couldn't do previously. But before we finish this video, I just want to really importantly talk about the unit vectors. As with 2-dimensional space, in 3-dimensional space, we define 3 unit vectors. Unit vectors are just vectors that have a magnitude of 1 and go in exactly the same direction of one of our axes. In this case, we have I, j, and k. We have the vector I is the vector that goes directly in the same distance as the x-axis and has a magnitude of 1. J goes in the distance, the direction, of the y-axis, and has a magnitude of 1. And k is the vector that goes directly parallel to the z-axis and also has a magnitude of 1. In other words, I is simply in component form 1, 0, 0. J is in component form 0, 1, 0. And I'm sure you're getting the idea right here. K then would be 0, 0, 1. There's a lot of important reasons for having and defining these unit vectors, but one beautiful application is if we have, let's say we have this vector as in our last example here, and it is 7, negative 7, 5. We can actually describe that vector using the unit vectors and the concepts of scalar multiplication and vector addition as saying the vector v is 7 times I minus 7 times j plus 5 times k. And again, it shouldn't take much for you to see that if we performed all of these operations, given these component definitions of I, j, and k, we would end up with this vector v.